order to get what the action of L is, what do I do? Well, I find what the action of T is inside the correlation function. Then I multiply this action of T by Z to the power n plus 1. And I integrate dz divided by 2 pi. Right? Because all I'm doing is isolating the part of that correlation function that behaves like 1 over z to the pi n plus 2. And there's a lovely way to do that using Cauchy's theorem. Is this clear? Okay. Now, you remember we said that the action of L might depend, is given by this kind of path integral, this kind of integral, but changes. Depends on whether there's that you can't just go through operator insertions.
So the detail might be clear.
Yes. So we're in the Z plane. Okay. We've taken a slice of constant time. L is some operator defined at some time. And if I want to insert L at that time, what do? I use the definition. Okay? I insert T everywhere on the circle and do the following contour integral on correlation functions of T. That will give me correlation functions of L. Is this clear?
And what was the statement of the operator insertion?
Yeah. So the statement about the operator insertion was that if you insert this thing here or you insert this thing here, you should get something different. Why is that? Why is that something?
Correlation functions change every coordinates.
Yeah, because correlation functions in a path integral are always time ordered. So if you put something before something else, you get one order. If you put something after something else, you get second order. And unless these two operators commute, you should get a different state. Okay? So, how do we see that in terms of this picture? You see, by Cauchy's theorem, provided this T here, provided the correlation function in question is completely analytic, it doesn't matter what contour we insert. Is this clear? Doesn't sound clear. Let's say. Suppose we have, every statement I'm making is a statement within a correlation function, inside the path integral. Okay? So suppose I've got some operator inside. Okay, I wanted to put L at some time. So I do this. What it means is the path integral, it means the correlation function of T with all these other operators. Thought of as a function of the insertion point of Z, and then integrated in this way. That's clear, right? Okay, now provided the answer, the correlation function is analytic in Z, I can, for all the values of Z for which it's analytic, I can freely deform the contour. It won't change my answer. That's Cauchy's theorem. For any analytic function, you can freely deform your contour in regions of analyticity. But you can't go through regions of non-analyticity and regions of singularities with this. Now we know that in general, T with other operators inserted will have singularities. Okay? So if you insert your L operator here, it will not be the same as inserting your L operator here. Because there will be a contribution from singularity that you've not taken into account. Okay? And that is the mathematical analog for the physical statement that time-ordered operators, the insertion of time-ordered operators depend, putting something just before or just after is different unless the operators communicate. Is this clear? Now I want to take this intuition and use it as a calculation device.
So the difference should actually
to the residue and should also be proportional to the commutator. Okay, so let's actually use this as a nice calculation of in order to calculate something of interest. So what I want to do is to take the definition we had of the LMs, which defines some operators on our elements. space. And I want to compute the commutation relations between these operators. Okay? So what I want to do is compute what I get when I take ln minus ln. By the way, what are these ln's? These ln's are the generators of various conformal transformations. You see that, right? We had a formula for the generators of conformal transformations last time. Okay? It was the current was multiplying epsilon of z with t of z. That was current, and if you wanted the charge, then you have to take this thing and integrate it over space, which is over the circle. Okay? So now, you remember we could parameterize conformal transformations instead of taking arbitrary epsilon z by taking powers of epsilon. So it's like some power times t of z, okay, integrated over the circle. Now, so if you perform z to the power k times t of z and integrate it over the circle, but t of z was z to the power k times ln divided by z to the power n plus 2 sum over n. We do this integral over the circle, it clicks only when k is equal to n plus 1. Okay, so you get essentially ln plus 1. So these ln plus 1s are the generators of conformal transformations, corresponding to the conformal transformation in what k, some link between k and n. Okay, so that's why we're interested in computing the commutation relations between these objects, because we've got a huge symmetry in our theory. Symmetry under conformal transformations. And we want to see what symmetry group the commutation relations of the symmetry algebra generate. So what we're doing is conceptually equivalent to computing the commutation relations of the generators of SU2 in a theory of computation. Okay, so let's go. This is what we want to compute. How do we do it? Well, let's see. Let's write down the expressions for Lm and Ln. The first thing we want to do is to ask, how do you compute Lm times Ln inside a path integral? Well, remember, inside a path integral, anything that's inserted at an earlier time goes to the right. Things inserted at a later time go to the left. Earlier times in z plane is smaller in S. Okay, so if I want to compute Lm times Ln, I should do the following. Remember, Lm was equal to integral dz z to the power n plus 1 t of z divided by 2 pi n. Ln was equal to, let's take w to the power n plus 1 by 2 pi I t of w. So, if I want to compute Ln times Ln, what I do is do this double insertion with two t's, one at w and one at z. Do two contour integrals where the outer contour integral is z and inner contour integral is v. Okay? So, let's make a final statement. Ln times Ln, the insertion of Ln times Ln is what? Is equal to the product of these two things, so dw dz by 2 pi I z to the power n plus 1 w to the power n plus 1 t of z t of w on this contour. Okay? On this contour. What is Ln times Ln? That is equal to dw dz 2 pi I the whole thing squared, and then the same thing, z to the power n plus 1 w to the power n plus 1 t of z t of w, but on this contour where z has moved inside it. contour do you need? And it doesn't matter. Because unless these two T's approach each other, the correlation function is analytic. By Cauchy's theorem, what contour do you choose? What contour do you choose? Unless you pass through and point of insertion of T, doesn't matter. Okay? So anything that is inside, any outside, whatever wiggly shape you take, doesn't matter. You can choose circles, but it doesn't matter. Okay, from the Hilbert space point of view, you wanted to choose circles. Once you've chosen that, you can deform it however you want. So let's deform it in a way that is of advantage to us. Okay, so let's see. Suppose I take W, and there are two integrals I have to do. I have to do the W integral and the Z integral. Let me first do the W, and let me first do the Z integral. So let me freeze W to a particular value. So I'll freeze W to a particular value here. I'll imagine that the W integral is always at on a particular contour, and the Z thing goes outside and inside. Let me freeze W to a particular value here. So at that value of W, I want to do the Z integral. So all I have to do is to be careful to avoid this point. Otherwise I can deform my contour to anywhere I want. Okay, so I can deform this contour to here. I've not gone through W, and I can deform this contour to here. I've not gone through W. But when I do this minus this, what integral am I doing? I'm just doing the integral W, this W point on here, and then the Z integral is just doing this. Okay, so in order to compute if I want to compute LM commutator LM, what do I have to do? Okay, after I do all this stuff, I still have to do the W integral. So I'll have to do dW divided by 2 pi I. Okay? And then, though, this part is very simple. Because it just picks up the residue of the pole and literally picks up the residue of the pole because I've got 1 over 2 pi I there. So it's just the residue of the pole of z to the pi plus 1 W to the pi n plus 1 T of Z T of W. So it's the residue of the pole in variable Z above W. Is that clear? Okay? So now that's very simple. Let's just do the calculation. Okay, we'll really stop at 5 minutes. We're going over time. Since Ajay has so nicely replaced the calculation, there's no pressure. Okay. Fine. So let's move on. How do we do the calculation? So all we have to do is compute the residue of the pole.
Are we having a seminar?
Yeah, I forgot to do that. Well, apparently, we were supposed to have it. I totally forgot it. But where is Open?
Just waiting in this room, and I came several times and then.
I'm so sorry, sir. Can we just have it now?
So.
Why not? No? Yeah, we have to wind this up basically. Yeah. Okay, let's wind. Okay, let me leave as an exercise for you to compute this residue. Okay, we'll allow somebody to come to the board and do it. Okay, so we stop with it. Okay. However, dealing with that string is technically complicated.